This is the third day of the Mathematics of Condensed Matter and Beyond conference hosted by CAMS AUB in Beirut. I hope that you all enjoy this long day full of interesting talks. And as usual, questions to speakers will be held at the end of each talk by raising hand to be unmuted. So thank you so much for attending. And we are happy to start our day with Bernard Helffer, University of Nantes, who will give a talk titled Spectral Theory for the Bloch-Torrey operator. Welcome, Bernard.
Okay, thank you very much for the invitation. So I have a problem with my first page. The title has disappeared. So I will mainly speak about common work with Yanni Valmog, and at the end also with a physicist, Denis Grebenkov, and his student, Nicolas Moutal. But one part corresponds to older works, which starts maybe with works by Yanni Valmog, then my PhD student, Raphaël Henry, and then a list of articles which I wrote together with Grebenkov, Valmog, Henry, and maybe I forget some names. So the first Bloch-Torrey operator that we look at was the very simple operator minus a square Laplacian plus I x1. And this was a particular case of a more general study that we have started with my, for example, with my student Raphaël Henry, of minus a square Laplacian plus I v of x. So this is a Schrödinger operator with pure imaginary potential. But this particular model, minus a squared delta plus I x1, is called, this I learned from this physicist Denis Grebenkov, is called the Bloch-Torrey operator. Actually, if you look in the literature, this Bloch-Torrey model, which here is considered as an operator, say in L2 of R2, or L2 of some open set omega in R2, so a scalar operator. But if you look to the original model of the Bloch-Torrey operator, it is actually a system, and it's a very simple system where you have minus the Laplacian acting tensored by the identity, plus the B of x. B of x is the magnetic field, which simply acts by the exterior product. And so it's a free by free system. And so I just reproduce the physical motivation without to certify that I understand all the words which are there. So, so this model describes the diffusion precession of spin-bearing particles in nuclear magnetic resonance experiments and helps in understanding the intricate relation between the geometric structure of the studied sample and the measured signal. So written in a physical way, the equation we are interested in concern the magnetization, and this is evolution equation, dt m equal minus gamma b times m plus a diffusion term d delta m. So this looks like a rather natural operator. And of course, we start from some evolution operator, but we will mainly, like we do very often for the analysis of this kind of thing, look at the associated semigroup and then look at the resolvent problem for the stationary operator on the right. Okay, so here gamma and d are specific physical parameters. But so in some sense, I am a mathematician, that I forget completely this physical parameter, and I just choose one parameter, which is divided by some constant. I just choose one parameter here, epsilon, and when quantitative results are concerned, I will look to what I know the best as the semi-classical limit, that is epsilon tends to 0. So then if you want to come back to the physics, you have to interpret this regime in terms of the various physical constants. Okay. So I just recall a few things about the simpler model, minus epsilon square Laplacian plus I v of x. And in the analysis of this kind of model, the first thing to do was to analyze linearized version. And typically, you replace v of x by the linear part. And what do you get? You get minus Laplacian plus I v scalar product with x, where v is a fixed vector. So in the case where you are in RD, you can assume that v is 1, 0, 0, and you get minus Laplacian plus I x1. But in order to analyze problem with boundary, you have to also to consider problem in R plus D, say, where I write x R plus D with x1, say, positive. And then it's important to keep this V, because the result will depend on the direction of V at the boundary. And so the spectral properties of this operator are relatively easy to analyze. And you first start with the two results in dimension 1. And in dimension 1, if you are in R, you have this model, the so-called complex Airy model. And the result is that the spectrum is empty. Now, if you look at the model in R plus, then you get a discrete spectrum, which is along a line in a complex, and which are directly related to the zeros of the Airy function. So you have two models, one model where the spectrum is empty, and another model, in the case with boundary, where you have a sequence of eigenvalues tending to infinity along a line, a ray in the complex. Now, if you come back to the general situation, so I will come back to this a little later. But if you come back now to the general Torrey situation, with then the problem looks more complex, and you have many questions to look at. And in particular, so first you have to define what is your closed realization, first in R3 and then in the case of a domain. And you can ask all the questions that appear in the scalar case. Is the operator maximally accretive? Can we characterize the domain of the operator? When do we have a compact resolvent? Can we localize the spectrum? And in view of the analysis of the decay of the associated semigroup, we should ask, can we control the resolvent? It's not enough, because we have a non-Selfadjoint problem. It's not enough to localize the spectrum. We have also to establish resolvent estimate if you want to come back to the semigroup. And so it appears that if there was a huge literature about this model, we are not aware at the moment of many results for the more general situation. And so just to begin, before to treat more general question, let us look at simpler situations. And the first is a model which is 1D, which appears if I assume that the magnetic field B depends only on one variable. So say the variable x1. Then it's natural to make the Fourier. Sorry, I have a problem with the window. Excuse me. So in this case, you can do the partial Fourier transform in the x2 and x3 variable, and you get a one-dimensional system, 3x3 system, which looks like this. So essentially, the term on the diagonal, if you are looking at spectral problem, you can assume it's 0 because you can shift these terms in the spectrum. And then what do you get? So you get, so you have this system, and so you try to do what you were doing in the standard scalar case. You linearize B. But here, beta naught is important. And so when beta naught equals 0, there is a big simplification. We will see this below, because it means that the direction of the magnetic field is fixed. And there are already difficulties in the case when beta naught is not 0. And this is one of the model we will analyze in detail with Yanni Valmog. And if the localization of the spectrum is not too difficult, the proof of resultant estimates will be quite complicated. Okay, so this is the first model, and the second one is to consider the case where the direction of the magnetic field is fixed. And then, because it's, of course, if we think of our magnetic field, we can think that we are in R3, but if we think of a magnetic field which should be closed, you arrive easily to that it should be a function of two variables, x1, x2. And then the skew symmetric matrix associated with this B exterior product is takes this form: 0 minus B3, B3, 0, 0, 0, 0. Okay? And then in this case, if you change the basis of C3, then you diagonalize your operator, and it takes this simple form: minus epsilon square Laplacian plus IB3, 0, 0, 0 minus epsilon square minus IB3, and 0, 0 minus epsilon square delta. So it's a good way to understand in this simpler case what kind of result we can hope. First, you will have some continuous spectrum relative to minus epsilon square delta, so R plus. And then we have these two operators, which looks like the scalar case. And so this is probably for this reason that the physicists start to look at this simplified Bloch-Torrey model. Okay. And then, so in this case, you can at least, so this small m is a big M. In this case, you can apply separately to each of these operators all the analysis that has been done before. And here I I mentioned already the name, but here are the times where it was done. Almog 2008, Henri 2015, Almog Henri 2016, and then we have various contributions between 2016 and 2020, depend analyzing various cases. Okay. Okay, this I can. So, so you see that it's rather natural to consider the spectral property of this kind of operator. So this kind of operator enter in a larger class, which has the form minus delta times identity plus a matrix M. So the main interest for us is the case where it's fully antisymmetric, but you can also consider more generally matrix that you decompose into the self-adjoint part and the anti-self-adjoint part. And so most of the results we have in this part with Yaniv Almog are relative to rather general metrics, but I will, to simplify the presentation, I will limit myself to the restriction of this result to this Bloch-Torrey case. And so let us describe various results. First, the result about maximal accretivity. And then, so the question is that you start from C0 infinity RK RD, and you assume assumption 1, which is simply the positivity of the symmetric part, which is clear if this symmetric part is exactly identically 0. So you have always to think to what we have done for minus Laplacian plus IV. And so, so there is for minus Laplacian plus IV, there are criteria. And so I recall rather standard statements. For example, the first, when V is real, self-adjoint case, this is the question of essential self-adjointness. And so it's known that if V is positive and has enough regularity, minus delta plus V is essentially self-adjoint. Now, if you look at least the proof which we gave in a paper with Francis Nier, it's you can adapt the proof for treating, for example, the Fokker-Planck operator, which is typically non-self-adjoint, or the complex Schrödinger operator in this form. And so the result is without any additional assumptions, this is maximally accretive. So you don't need to put many assumptions. Okay, and so just under this, if the coefficients are regular and if you have the positivity of the symmetric part, you have a maximal accretive operator. So in this way, you can already have a natural close extension of the operator initially defined on function with compact support. And this is the operator that you consider for which you can use the standard theory of semigroup. Then the second thing, which is more specific about our problem, is do we have essential spectrum? And so there is something very special in the case when M of X is the exterior product with B of X, is that in dimension 3, you have always the kernel of the matrix M of X is always non-zero. And now to determine the essential spectrum, you only need the assumption outside the compact. And actually, you can make this assumption weaker. You only need this property for a sequence of balls of suitable radius tending to infinity. Now, if you apply this kind of criteria to our model, here is a simple result. You suppose that outside a ball, you have that the magnetic field is not identically is not zero, and that you control the derivative of order 1 and 2 by B of x, the module of B of x. Then you can show that the resultant is not compact. So this looks like this is a technical condition. The important thing is that in our case, we have effectively this, the dimension of K of M of x is at least 1. Because B of x itself is in the kernel. Okay, so then the result is that so the Bloch-Torrey operator, when k equal 3 and d equal 3, is not compact. And moreover, we can be more precise. We have that R plus is indeed in the spectrum of P. And so this is not completely surprising if you go back to the particular model I presented before. Where was it? Yes, when for this simplified model, you see that you have this term minus epsilon square Laplacian. But so this is true in a much more general. It's not only true for the model. Sorry, I go back. Okay. Now, a particular case which could be of interest is to look to some affine situation, and it applies when A is a non-zero D cross K matrix. But already the case A equals 0 is interesting. So if you compute the case where B is constant, then you see that the spectrum is R plus 2 copies of R plus shifted in the complex symmetrically. Okay. So the second, so this was the question of the essential spectrum. Now, when you define the maximal accretivity, the maximal accretive operator, so you have a first definition of the domain, but a natural question is to have a more effective description of the domain of the operator. And this is usually related to so-called maximal estimates. And this has been analyzed in great detail for initially already the question, you can ask the question for minus Laplacian plus V. Typically, if I have U in L2 minus delta plus VU in L2, do I know that minus delta U is in L2 and VU is in L2? This is the kind of maximal estimate. It's not always true. And so the same question is for minus Laplacian plus IVU. Do you have separate regularity in the two terms? So we have a right definition for the operator, but it does not follow immediately that you have this kind of regularity. And so here we show in this kind of theorem that this is indeed true under, again, some control of the oscillation of the magnetic field. So this first result is rather weak in the sense that you see we ask for control of the two first derivatives. It means that B of x will not has not the right to oscillate too much. The direction is not necessarily fixed, but you control the oscillation of B in a ball. So essentially, outside a compact, the oscillation of B of x is controlled in a ball. And here, under this assumption, you get that the domain of P is the set of the U in H2, such that B times U is in L2. So what you hope from the beginning, but this has to be proved. Okay. So this theorem, so it is what it is. In the next slides, I will show you a much stronger result, but under the assumptions that two of the components of B of x are bounded. And in this case, we will see that we can, so I assume that B1 and B2 are bounded. And then in this case, I can transfer the result I know for minus Laplacian plus I V of x, essentially applied to minus delta plus I B3 of x. I can transfer the information to get the characterization of the domain. So sometimes there is epsilon, sometimes there is 1. For this qualitative result, it's not important. It's enough to do the analysis for epsilon equal 1. And so here you see the result is much stronger because I just assume that there exists some R, and considering this quantity, I assume that the derivative with one more rank, so the derivative of order R plus 1, are controlled by this. So it's much weaker than the assumption I have in the former theorem. And again, the result is the same. We have maximal estimate. And here I give the proof because, so I will not give many proofs, but it's important to see from where our result could come. And so again, I make my change of basis of C3 to try to, in some sense, to diagonalize the system. And here is the matrix I get. And then minus, you get minus IB3, and then, so it's not, you cannot diagonalize, but the terms which are outside the diagonal are bounded. And then in this way, if you want to look at the question of domain, you will rewrite a system BU equal F in a system in the following form, where instead of F on the right-hand side, you have G tilde 1 equal F tilde 1 plus B1 minus IB2 over square root of 2 U tilde of 3. And so if you, in the first step, you don't need it. So U tilde 3 by is in L2. And then you have just to use the regularity statements for minus delta minus IB3 and the operator obtained by complex conjugation minus delta plus IB3. And so then all the proofs go rather easily. Okay. And so the result is in this new coordinate, you get that you have U tilde in H2, B3 U tilde 1 in L2, and B3 U tilde 2 in L2. Now, as I said, if you are interested in the semi-group theory, you need to have more and to have estimate for the resolve. And so what we know rather well from the previous studies is information about the resolvent of this model. And so we have to transfer the information that we have for this operator for our system. And so this is done in the same way. You change of basis, you rewrite the resolvent equation in this way, and then you go on. We assume that lambda is not in the spectrum of minus Laplacian plus or minus IB3, in order that we can introduce R plus or minus of lambda equal minus delta plus or minus IB3 minus lambda minus 1. And then, so this object is supposed to be rather well analyzed by the scalar analysis. And then we get for U3 this equation, which is in some sense the effective spectral equation, which is again scalar because it concerns only U3. And then, so if now you rewrite, you compose with the resolvent of minus delta minus lambda. So you assume that lambda is not in the spectrum of minus Laplacian. That simply, this gives you a condition on the imaginary part of lambda, or you assume that real part of lambda is negative. And then you get this operator, k lambda. So, and then the question is to relate the spectral property of k lambda with the known property that we have on minus delta minus lambda minus 1, very easy, and R minus and R plus. And so I will not enter too much in the detail, but there are many situations where we can have for the resolvent R plus or minus lambda an estimate of this type for various value of S. And then if we add this, we get a corresponding estimate for the initial operator B1 minus lambda minus 1. Okay. Now the next question could be the point spectrum. And as you have seen from the previous formula, the reduction to a scalar situation comes from, is obtained assuming that we are not in a plus union the spectrum of these two operators. And then the result gives that for lambda in omega, so outside the spectrum of the basic operator minus Laplacian and minus delta plus or minus IB3, lambda is in the spectrum of B1 if and only if minus 1 is in the spectrum of k lambda. However, if minus Laplacian plus or minus IB3 as compact resolvent, then we get that in omega, the spectrum is discrete with isolated eigenvalues of finite multiplicity. So it has some, it looks a little like in the talk of Constantine yesterday, where you avoid some Dirichlet eigenvalue, and outside you can analyze specific things. Okay. So, so a few remarks. The proposition before, one possible assumption was that the C bar R plus lambda C is compact, and so in general it's not the case. But in the case k equal 1, And if you take B3 of x equal x, then you get this complex Hardy operator minus d2 over dx squared plus ix. And this is okay. And in addition, we are in a case where the spectrum is empty. Recall the result about the model. And so in this case, this omega becomes simply C minus R plus. So you get a discrete spectrum outside the real line. Okay, and then if you want to now go further, you have to do a quantitative estimate. And so I reintroduce the parameter epsilon. And so in this case, the paper we have written recently concern only k equal 1 and b1 equal constant and b2 of x, b3 of x equal x. And it's already not so simple. And so I will just show you the kind of result which we can obtain. So I repeat, I am in one dimension, and I look at the 3x3 system. I take the exterior product by b of x, and b of x as simply this simple form 1, 0, x. Then first, localization of the spectrum when epsilon tends to 0. Then the main approximation of this eigenvalue is given by I plus 2n minus 1 over 2, 1 plus I epsilon. It's parameterized by a non-zero integer. And then the results are the following. First, two abstract remarks that the spectrum is symmetric by complex conjugation. But so this is related to the structure of the operator. This operator is real. It sends real function on real function. And secondly, as a corollary of a previous statement, R plus is in the spectrum. And now I look outside, so these values are outside the real. And then I say that in a small ball of size epsilon square, around this value, I have some element in the spectrum. Okay. Unfortunately, the epsilon small enough depends on the number of balls you want to consider. So this is not perfect sense. I take a finite sequence of such eigenvalues, and then I have balls of size epsilon square, such that for epsilon small enough, I have eigenvalues. So this one is based mainly on construction of Casimodes, but you have always to be careful with Casimodes because we are in the non-self-adjoint case, so you cannot avoid to control the more stronger objects to show that corresponding to a Casimode, there is effectively an eigenvalue. And the second statement is less sympathetic in the sense. It's about estimate for the resolvent. And so we have estimate for the resolvent outside balls, the balls which I have defined before, with some radius. I avoid, so I remain with small real parts, and I avoid the real line. And then in this kind of region, I can have the estimate a rather complicated estimate for the resonance. So you see that there is this 1 over imaginary part of lambda square. So this is not self-adjoint. So you have a much worse estimate, and so and it's not so good as epsilon tends to 0. Okay. So how much time do I have?
5 minutes.
5. Okay.
Yeah.
It's very short. So,
but if you need 3 minutes only more, it's okay, of course.
Okay, I would prefer to have 10. Because, so the second part is, at the moment I just spoke about the case where the domain was RD. And so now it's natural to put a domain, because this is the real problem, and you can discuss about all these questions with a domain. So when you have a bounded domain, you lose a lot of problems, in the sense the compact resolvent is automatic and so on. But we can also look at exterior problem where the question is still present. And then, so essentially, we have not done with Yanni Valmog in this case of system, we have not done new analysis. And so I send you back to what has been done for minus epsilon square Laplacian plus IV. So there are various problems which are solved. Initially, we can start from Dirichlet, but you can analyze Neumann, Robin problem, exterior problem, and this has a real physical motivation if we refer to the origin of the Bloch-Torrey operator. So the Dirichlet condition is not apparently the most physical the most physical condition appearing in the physical question. I just mentioned one statement, which is rather old, at least for Dirichlet, which consists in analyzing the bottom. By bottom, I mean the most left eigenvalue, considering the real part. So you look to the real part of this, the real part of the spectrum and the infimum in the semi-classical limit. So my epsilon is now h, and then these are this kind of result that you can relate the bottom, this bottom of the real spectrum, with the first zeros of the Airy function. And you can also get rather precise estimates for the resolvent. Okay, and one important thing is that the localization of these first eigenfunctions, which lead to this bottom, corresponds to eigenfunction which live at the boundary of omega, and more specifically at the points where the gradient of V is normal to the boundary. And this can be understood by the analysis of minus Laplacian plus IVX in R2 or in R2 plus. So in R2, the spectrum is empty. And this explains why the particle should be localized at the boundary. You have, for the linearization of the model, you have no spectrum. Now, if you look at the boundary, so at the boundary, you get a model of this type, where V is the normal to the. So you have two vectors, you have nabla V and the normal. And so in this model, I have chosen that the normal is 1, 0, and I have nabla V. Now, if you look to this model and apply what we know for R and R plus, then the spectrum is empty all the time, except if V is 1, 0. Because when V is 1, 0, you have minus d2 over dx1 square plus ix1 plus minus d2 over dx2 square. And so you have spectrum. In all the other cases, the spectrum is empty. And this explains the localization. Okay, so this was the first half part of the talk. And so it remains 5 minutes for explaining a more recent example. I come back to the scalar Bloch-Torrey operator, but now I consider periodic structures. That means I look in R2, but I am outside the union of balls, which are or disks, which are transferred by periodicity. And so the question is, what can you say in this case? And so we have written a first result with. So I think this was motivated by a paper by my colleague physicist, where they were performing a rather formal computation to guess results, and we have tried together to see if what can be transformed in a mathematical proof. So I have not so much time, but I just wanted to ask questions. Maybe this is partially because we don't know all the literature. But the main question, the initial question is, in this kind of problem, we want to do Floquet theory. And so there are two different, so first question is, what do we know about Floquet theory, say for the standard periodic problem when the potential is not real? And so, of course, the Floquet decomposition exists because it's just related to the actions of some discrete group. This exists, but can we relate all the time the spectrum of the operator with the union of the spectrum of the reduced Floquet operator? And so I have only a partial answer to this. And so I have not seen many literature. The other things is in the Selfadjoint case, you have a band theory. The spectrum is consistent in band. So now if you go in the complex, what is going on? Is this band just simply deformed in the complex? Or does it appear new phenomena that is this band could become a closed curve? So, and the third difficulty, which is specific to the Bloch-Torrey operator, is that we are not in a periodic situation. We are in a periodic situation in the x2 variable, but in the x1 variable, when you use the translation, ix1 become ix1 plus I constant. And so and the last question, already we don't know if the spectrum is empty or not. If you are in the line, in the R2, the spectrum is empty. So now if you put, you look outside of this disk, so is the spectrum non-empty? So this is what we have tried to do, and so I think I will stop here. So we have positive answer at some of the questions, but I would like to emphasize that simply already in dimension 1, if you have minus d2 over dx squared plus v of x, where v of x is not real, Do you have a complete analysis of this problem in using Floquet theory? It's for me, it was unclear. I have models where I can show various things, but the simplest question about the spectrum in this case are still open, I think. Take minus d2 over dx squared plus I cosine x, for example. What is the spectrum? Okay, thank you very much.
Thank you very much, Bernard, for this interesting talk. And I hate this time restriction, but what can we do? Okay, so questions?
May I?
Yes.
Bernard, some of your operators, say the simplest one, Laplacian plus Ix, they exhibit a PT symmetry. Do you use this property somewhere?
In the last problem, there is a natural question which is to relate. This is the question 3. Is there a link between the existence of a Weyl sequence and the spectrum? So in the Selfadjoint case, we have a necessary and sufficient condition which permits to identify the spectrum with the existence of Weyl sequence. So, in the non-Selfadjoint case, this theorem is wrong. But for our model, we have the property that if you look to the complex conjugation, gamma composed with the operator equal the adjoint of the operator composed with gamma. So this is not exactly PT symmetry, but this kind of property can be useful.
Okay, thanks.
Okay, so Ayman, do you have a question?
Yes, please. So my question is about the eigenvalues kappa n.
Yes.
So may you show us the slide?
Yes, the slides, yes. This one?
So, yes, this one. So there is here a part 2n minus 1 over 2 times a constant. So is this the eigenvalue of some toy operator? How they arise? I mean, how you guessed them? If you want.
Yes, so I am not prepared the detail. Let's see. So the idea is so this is related to what we do. Sorry, here. The reduction to a scalar case. So sorry, this equation. So so we start from a version of this. Maybe change a little in the sense that I multiply by I compose with minus delta the composition of the product of these two operators, and then I try to construct a Quasimode for this radius operator. And so at the end, I get some complex harmonic oscillator. And so the value that appears are related to a complex harmonic oscillator.
Okay, thank you.
This part is relatively easy in the sense you can say in 3-4 pages see the construction. The difficulty is then to show that near these values we have effectively a real so not real, an eigenvalue, which exists. For this, you have to control the resolvent along a disk, along circles around each of these eigenvalues to show that the projector that you have cannot vanish, that you have effectively some eigenvalue there.
Okay, and I have another question on the
I don't.
When you prove the asymptotics on the bottom left eigenvalues. So if you show sides.
Okay, sorry, I have not heard the beginning of your question. There was a cut about the way we get this kind of estimate.
Oh, about when you obtain about the bottom of the left spectrum.
Yes,
that's this one. That's this one. So you passed on it. So,
after or before?
I think before.
So what is the idea? The idea is that at each point, so you have your omega,
so I ask you my question.
Okay.
So is there a formula for a variational formula for the real part of for this infimum? I mean, or is something else?
So there is some behind this. There is some approximate eigenstate, which is a model starting from the approximation of the operator at the point where nabla-V is orthogonal to. And so the model is the following. Minus d2 after changing of coordinates, minus d2 over dx1 square plus I x1 minus d2 over dx2 square plus I x2 square. So you have a complex harmonic oscillator in the other direction, and in the x1 direction you have the complex area operator on R plus. And so this gives you essentially at least formally you get in this way the most left eigenvalues. And so you do that for any point of this type. So in the basic case of the disk, you have only 2 points where nabla-V, if you look to minus delta plus I x1, you have only 2 points where this occurs. And you have some symmetry in the two problems in this case.
Thank you very much.
Thank you, Ayman. And unfortunately, maybe there is no room for more questions, but let's just check if we still have maybe one question if someone likes to ask, and we conclude. So, no, apparently. Thank you so much, Bernard, again.
Thank you.